So today we'll be talking about the IPEBB, the Integrated Power Electronics Building Block Capstone Design Project. Yeah. So our technical directors are Dr. Yonho Chung and Shu Senseng, and yeah. So our team is composed of four members: Gianni Smith, Max Bongiovanni, Justin Smith, and Patrick Felice. And just a little bit of a company overview. So there's three current projects going on at the same time. So the real-time simulator and educational laboratory for advanced electric transportation technologies, as well as a novel power conversion system and power management control for water monitoring stations, as well as the hardware accelerated machine learning EDA for integrated power electronics. Yeah. So our ultimate project motivation was to design an efficient power conversion system. So we were tasked with the problem of having so as you may know, batteries for drones, they the battery voltage will drop as it ends up discharging, which can lead to inefficiencies in the power conversion from the input to output, and as well the motors and ESCs will end up getting weaker over time due to this reduced thrust and um, yeah, and so our our solution would be to end up connecting multiple synchronous boost converters in series to maintain a stable voltage level. And this is our anticipated best outcome. On the left-hand side, you can see the image. So one IPEBP is equal to one synchronous boost converter. So these would all be connected in series and be controlled by one of the digital controllers. And yeah, so for the 6S, it would be three of them, and 4S, it would be two. And so, so our anticipated best outcome was to optimize the RL-based PEDA framework. Um, and as well extract the design parameters from the reinforcement learning based PEDA tool. And so the main thing, our main goal was to implement these and obtain the best values to obtain the most efficient converter. Although we didn't meet our goal for the ABO, and we ended up working more on building the converter, working on the closed loop control, and so on. And yeah, so some of our key technical accomplishments towards achieving this ABO were the drone assembly, circuit topology design. As well, we ended up building the first prototype, testing with the single boost converter with the quadcopter connected. We have the first PCB designed and the closed loop control using the C2000 digital controller. Yes, so the economic impact for the company, so it opens us up to commercialization with patents and licenses, as well as industry efficiency. So ultimately leading to decreased costs. Yeah, and yeah, here's just one more, just showing the simple block diagram of the whole project. And yeah, so my technical accomplishments include helping and assisting with the boost converter power stage design. So I ended up designing an open loop simulation in PSIM and validated the functionality of the converter as well. I ended up calculating the component values, generating Bode plots, transfer functions, and MATLAB. And then the second main thing for my contributions would be building and testing the boost converter stage. So I collaborated with the other with our team on building this and testing it. So um, we ended up testing the first prototype and then varied it under different load conditions up to 100% load. And then yeah, we connected it with the quadcopter and tested as well, and then got similar results as with the standalone converter. As well, we ended up building and beginning the testing on the PCB board. And yeah, so ultimately we started off the fall semester with the idea of using an LLC resonant converter. As you can see on the left-hand side, we have it has ultimately five different stages: the inverter, resonant tank, transformer, rectifier, output filter, and ultimately with the goal of achieving a boost gain. So we were going to operate in the inductive region, and yeah, So as we went on to design this, we later realized that we hadn't achieved this boost gain goal or gain graph. We ended up ultimately designing a series resonant converter, which is the same. We would be using the same topology, just it would be a different operating region. Um, yeah, and we ended up building this series resonant converter. As you can see on the left-hand side, the inverter stage is on the left, and then the resonant tank and the rectifiers on the right-hand side. And then, yeah, on the right-hand side, you can just see our test setup. But this is where we ended up running into a problem where we realized that we couldn't achieve 15 amps. Like, so we couldn't go past, I believe it was about 6 amps or so. Yeah, and so we decided to end up ditching this idea and going. Oh yeah, here's also some of the waveforms that we were able to see under no load condition. Yeah, so we decided to go with a new topology. We decided to go with a boost converter, but not only a boost converter, we decided to go with a synchronous boost converter as it can lead to higher efficiency, leading to lower conduction losses, better lower voltage performance, and yeah, it can also support higher output currents. And yeah, so with our design in mind, we decided to go with uh the putting the synchronous boost converters in series. So ultimately, as you can see here, there's only one battery. Although in the real case, it would be for the quadcopter, we would end up having two batteries. So each of them are about 6 volts input, and then the output would be around 16 for this one. And then with the other one, it would be three 6 volt batteries connected in series, and then that would be 18 volts on the output. Yes. And yeah, so continuing on, so yeah, we have this is ultimately our hardware circuit for the series resonant boost converter or series boost converter. So it'll ultimately be connected to a battery, which then is connected to the flight controller, and then that is also connected to the ESCs and motors. And yeah, we can also do the same thing with the hexacopter version as well. And yeah, so here's just a brief overview of our design of the boost converter. So here we have the duty cycle. We ended up calculating the current and the current change in the inductor, and then the inductor value, and then the peak switching current, calculating the output capacitor value, and yeah. So continuing on, I ended up doing the open loop simulation in PSIM. So as you can see here, it's ultimately the same as the previous slide with the converter topology, and yeah. And right here we can see that we have yeah, some of the simulation results. So in the top you can see the high and low side gate signals, diode current, inductor current, output voltage, and output current. Yeah. And here's the Bode plot. So we ultimately, after doing the Bode plot for this design, we ended up showing 55.7 degrees phase margin for this. And then also I was able to generate uh, the different graphs for the output impedance, asymptotic gain, and closed loop output impedance. And we were able to calculate the poles and zeros as well as the DC gain. And yeah, now I'll be giving this over to Patrick. Thank you.
Thank you, Gianni. My name is Patrick. I was part of the hardware team for the IPEBB capstone project. This is just a simple block diagram of our entire project. My technical accomplishments consisted of helping out Gianni and Max with the boost converter power stage design, just meaning um, we have the boost converter that consists of capacitors, inductors, and in this case, two MOSFETs, and kind of choosing the appropriate input output caps as well as the appropriate inductor that we will be using for our specific application. And then my second technical accomplishment was just testing and troubleshooting the boost converter just to make sure it functioned as intended. As far as physical implementation of the boost converter, first we started off with the prototype in Figure 14. You can see two different boards. First being the left board just represents a full, or sorry, a half bridge configuration of the switches. So we didn't really design this board. This was given to us by our TDs. This is originally a full bridge, but since we aren't using a full bridge for our application, we can just use two MOSFETs. As you can see by the heat sinks, MOSFET 1, MOSFET 2, and then an input cap. Um, Pretty simple. Obviously, there's some components here, like a bootstrap circuit that takes 3.3 volts in and feeds a 12-volt square wave to the MOSFETs for their switching, obviously with their respective duty cycle. And then we have our designed inductor, and then we have that voltage being supplied to a output cap, and then on the right side of this output cap is our load. In this case, our load would be the quadcopter. We did this initially just to make sure that our design actually works and that we were able to step up the voltage like we wanted it to. And then figure 15 is just we were able to use a PCB or just use Altium to design a PCB of the boost converter to make it look more aesthetically pleasing. So we don't have these red and black wires just hanging out looking a bit strange, especially if we were able to show this at the symposium or the capstone summit. Um, and here we're just probing different things. Like this scope is to measure the inductor current. This is to measure the output voltage. This is to measure the signal of the gate and source of the high side MOSFET. And here we're using a differential probe since this source connects to the drain of the other MOSFET and not ground. As far as physical implementation to the quadcopter, here we just have our battery VN. This is also supplying 3.3 volts that's used for the C2000 digital microcontroller from TI, as well as our boost converter here. But we weren't able to uh, implement the actual PCB just because we were still waiting for the PCB to come in. And we weren't sure if it was going to come in on time for us to do actual testing. So for now, we just have this prototype that we made. But either way, we tested the boost converter, which I'll talk about in a couple of slides. And yeah, we just swapped that out. And then we have here our quadcopter drone, which is acting as our load here after this output cap. As far as experimental results, first we want to first obviously program the microcontroller with 3.3 or program the microcontroller with their duty cycle. And here in figure 17, we can see that that's the gate signal that's coming out of the microcontroller. The purple slash pinkish represents the high side and the green represents the low side. So the pink would be fed into one MOSFET, the green would be fed into the other MOSFET, etc. And then we would send this figure 17 through a bootstrap circuit that would take it from 3.3 volts to 12 volts, which you can see in figure 18. This figure 18 is the actual gate signals that are being fed into the MOSFETs for their on and off switching. So we were just kind of confirming that, yes, our bootstrap circuit is working as intended and that there were no issues with the bootstrap circuit. As far as experimental results part 2, we were able to, again, do the high side and low side gate signals, as well as the output voltage is what we care about, as well as the inductor current. So we were able to do that for different load conditions. 10% load just meaning if you have, for example, in this case, a 50% load a 15 amp load that we want to achieve, 10% of that would be whatever, right? And 100% of that would be 15. So that's what we're trying to do, just do different load conditions to see how the circuit behaves. As far as efficiency, we were able to do different load conditions from 10% to 100%, and we were able to measure the efficiency of the entire converter across the entire range of the load condition. So at 15 amps output current, we would have about 87%. At around 7.5 amps, we get 92. So this is overall a really efficient converter. Obviously, we can make some minor tweaks, um, like component selection, choosing different MOSFETs that have lower RDS resistance turn on values, because the lower the value, the better efficiency we can achieve, as well as kind of doing the calculations on different MOSFETs for switching to see which MOSFET gives a better switching loss, as well as for the output cap, maybe a lower ESR value for our caps would be better for more efficiency. And then figure 22 is just the heat dissipation of the MOSFETs under full load is what we really care about, because it would be operating at max, and we just want to make sure that our temperature isn't too high to where it would potentially be harmful for our circuit. And now I'm going to pass this on to Max. Thank you.
Hello, my name is Max Bongiovanni, and I will be talking about the parameters of the boost converter, as well as the development of the PCB for the boost converter and the assembly of the actual board itself. My technical contributions this semester to the project were to design the PCB. I used a PCB design software called Altium Designer in order to design the PCB of the boost converter. And my other technical contribution was the assembly of the boost converter. I took all of the components from the BOM list and I soldered all of them onto the converter itself. And then I tested the converter on the drone itself to make sure that it works. So the parameters of the drone are based off of these three things. The input is based off of this battery, the HRB 6-cell lithium polymer battery, as well as the Kakute flight controller and the DJI E800 motors, of which there were 4 since we're using a quadcopter. This is what the PCB looks like on the 3D view for Altium Designer. The PCB in length is about 17.5 centimeters, and in width it's about 13 centimeters. This is what the PCB on the left, this is what the PCB looks like with all of the parts soldered onto it. And we included a spot for the Texas Instruments digital microcontroller, which is it's going to be our control system, but Justin will tell you all about that. And then on the right, you can see 2 of them actually, because we assembled 2 boards, 2 IPEBs, and they're meant to be stacked on top of one another for when we put them in series with each other or in parallel with each other. That'll be all from me.
Hello, my name is Justin. So the rest of the team already discussed a lot about the converter and the drone we used for the project. As a computer engineer on the project, I primarily focused on the controller for the converter. So my technical contributions included designing 2 microcontrollers. One is for a resonant LLC converter, and the other one is for the boost converter. The boost converter is the one we actually ended up going with, so that's the only one we're using. But I did design 2. They're both PI controllers that operate similarly, with one difference between the two. The LLC controller adjusts the switching frequency of the LLC converter to keep it at a constant output voltage, and the boost controller adjusts the boost converter's duty cycle to keep it at a constant output voltage. This is a picture of the Texas Instruments microcontroller we used for the project. So this diagram can give you a pretty good high-level understanding of how the entire system works. Everything in blue could be considered to be the controller. The controller takes two inputs. These are the two green ones. First is a reference voltage. This is a constant value hard-coded into the controller. Ours is currently set to 16 volts. The controller also is in real time taking a constant voltage input from the boost converter. Compares these two voltages to calculate the voltage error. This is then sent to the PI controller, where some relatively simple math is done that calculates a new signal. The signal is sent to the PWM generator, which sends a signal back to the boost converter, changing its duty cycle in order to keep a constant voltage output. The brains of the controller are really done in the interrupt service routine. This is the ISR.c file. This function gets called regularly from main.c. To begin, we take the voltage input through the ADC pin. We can't take an input of 16 volts, otherwise the controller would explode. So we scale it down using a voltage divider. This input line scales it back to our desired value. Next, we calculate its error and do some other PI math, finding an integral and calculating a new duty. This is then clamped for added stability and sent to the PWM output, which is sent back to the converter. Here are some tests I ran on both the controllers to verify their functionality. They both worked pretty well. The one on the right is the output for the LLC converter's controller. It is able to keep a constant frequency of about 115 kilohertz, which corresponds to our desired output voltage, and it has a dead time of 100 nanoseconds to protect the MOSFETs on the converter. On the left, we have the boost converter, which also looks similar to the LLC controller, except this one is modified using duty rather than frequency. It has a clean square wave and also a 100 nanosecond dead time to protect the MOSFETs. We would like to thank our TDs, Professor Zhang and Shushan, for their guidance throughout the semester, as well as we'd like to thank Dr. Sunak for the opportunity to work on the project. Thanks for your time.